Cool, we'll go ahead and get started. So our first talk today is via Zoom because our wonderful speaker, Isabella, is over in France, and it was a little far for her to travel. But the reasoning was when we were thinking about oddities, I immediately thought of trapezy textures, and which you may have seen them. They show up in several different minerals like emeralds and in corundum, sapphires, and rubies. And it's just a really funky texture that I personally don't really understand. And I was thinking it'd be really interesting to get somebody to speak on that topic. And so I was doing some research online, and I could not find anybody who is an expert on trapezy texture anywhere on this continent. And I was looking on Google Scholar and various other places, and Isabella's name kept coming up on all the most interesting looking papers. So I thought, okay, I just got to ask her if she'd be willing to present. And luckily we now have Zoom, and it should go relatively smoothly as long as the internet holds up for us. So I'll do a little introduction for Isabella. So Isabella Pignatelli, I hope I'm pronouncing that correctly, is an assistant professor at the University of Lorraine in Nancy, France. And she did a PhD in Italy on crystallography, followed by postdocs in both France and at UCLA. And she's primarily focused on the links between the composition and structure of minerals and overall how they form, their formation and all those mechanisms. So we're really, really excited to hear all about trapezy texture and oddities in Colombian emeralds from Isabella this morning. All right, now I will turn it over to you now and mute myself. Okay, we should be good for you to go ahead and start.
Okay. Good morning. Thank you for your nice presentation. And thank you for the invitation. It's a pleasure for me to share two results from my research about Colombian emeralds with you. So today I will show you trapezy emeralds, and those other particular samples also come from Colombia. So firstly, let me remember you what beryl is. Beryl is a silicate where silicium form tetrahedra, and the tetrahedra are connected to each other, sharing oxygen atom and forming a ring. These rings are stacked along the C crystallographic axis, and this is why, as you can see here, the typical morphology of beryl is prismatic elongated in one direction. And then the tetrahedra are connected laterally by other polyhedra. You have here the tetrahedra filled by beryllium, and you also have the octahedra filled by aluminium. But what is important? If the aluminium is not replaced by few amounts of other cation, you cannot have the color variety of this mineral, but the beryl will be colorless. So if you want the variety that are famous in gemology, you should have substitution. For example, if aluminum is replaced by iron 2+, you will have the blue color. Or if it is replaced by manganese, you will have morganite. And today we will focus on the green variety that is, of course, you will know it's called emerald, and is done results by the aluminum substitution by chromium and vanadium. In particular, today we focus on emerald coming from Colombia. Why? Because there are very particular samples that come from this place and only from this place in the world. In Colombia, the emerald formation is not associated with a magmatic activity or magmatic event, but they are found in sedimentary rocks that you can see here, the black one, and they are called black shale. So this is the first important feature of these kind of deposits. And the other important thing is that in Colombia we have a complex geological history who will explain why we can find these rare and particular samples, including trappist emeralds. This geological context is um, strongly affected by the circulation of hydrothermal fluids along tectonic structure and lithological contact. But these fluids also created overpressure in black shale, and this overpressure will cause later the hydraulic fracturing and the breccia formation, as you can see here in the picture here below, and as well as the opening of veins where the emeralds will precipitate with other secondary minerals. But a key role in this sedimentary basin is played by evaporites that are present in the black shale. Why? Because the fluid circulated in this basin will dissolve the evaporites and then they became rich in salt. So they became what are called brine. And this is testified by the multi-phase inclusion that are typical of Colombian emeralds. As you can see here, you have a liquid, you have a bubble of gas, and you have cubic crystal of halite and sometimes of silvite. So this practically show the presence of salt in this fluid. Dissolving evaporites, the fluids will become rich in sodium and calcium. This will lead to the formation of calcites and albites. And the process due to the precipitation of these minerals is known in literature as albitization of black shale, because the black shale became whiter due to the precipitation of these minerals. So at the beginning are black, but when they are alterated by the fluids, they will become white. Another important phenomenon in the process in these sedimentary basins is the thermal reduction of sulfate by organic matter. Why? First of all, because the thermal reduction of sulfate will interact with the black shale, releasing vanadium, chromium, and beryllium, which, like I said you before, are the main important elements to have burial. And also because the thermal reduction of sulfate will produce H2S, so which will promote the formation of pyrite. And you can see here the precipitation of emeralds with a big crystal of pyrite. So here the emerald is included in pyrite, showing that they form almost at the same times. And why pyrite is important in Colombia? Because, as you can see here, pyrite will keep the iron from the system, from the medium groove. So the emeralds will contain only chromium and vanadium, resulting in a particular green color that is known in jewelry, in gemology, like muzo green, because it's a green so particular that looks like the grass and is easy to recognize between the other green emeralds in the market. So, say that we can have in this basin that is called Eastern Cordillera basin, two belts, the Eastern belt and the Western belt. The two belts are geologically different, and these will help the formation of a different kind of emerald oddity. For example, here we can in the eastern belt we have extensional structure, geological structure. So we cannot find trappish emeralds. We also found vaso emeralds, gastropods, spongy emeralds, scepter emeralds, spear-shaped emeralds, fibrous emeralds, but no trappish due to the geological situation. So now I will start you with these particular symbols found in the eastern belt, and then I will explain you what we can find on the other side of this basin. The first sample you can see here is the scepter emerald. This is the unique sample known until now for emerald. Of course, you can have scepter sample for quartz, for example, but for emerald is the only one known. And like in quartz, it is characterized by two portions. The upper one, that is the cup, and that is stubby and larger, and the thinner one, that is the trunk. Between them, as you can see here, you can have the accumulation of solid inclusion that here are quartz and pyrite. And in the two portions, we also observed the multi-phase inclusion, similar to those I mentioned you before and typical of Colombian emeralds. I mean the fluid inclusion, which we have the cubic phase of a light, the liquid, and the bubble of gas. These are very typical of emeralds coming from Colombian deposits. So they are they are used generally to confirm the occurrence, the localities where they come from. Of course, this sample cannot be destroyed, so we are limited in the use of analytical technique to analyze them. And we use the X-ray tomography because it's not destructive one and allow us to have a three-dimensional view of what is inside this kind of sample. And you can see here in the first image you have a lot of voids, a lot of cavities that are concentrated above all in the cap and around the solid inclusion. And here you can see the solid inclusion, which are the gray one are quartz and the white one are pyrite. So you can also see that the cavities, the fluid inclusion are just at the beginning of the trunk, but they do not develop inside it. Thanks to this technique, we also see that the cap protrudes laterally from the trunk, and we have a kind of step on the surface that is not smooth. So, by analogy with the quartz, we can say that it is formed by epitaxy. But as we have a solid inclusion separated in two portions, there is a special kind of epitaxy that is called epitaxial lateral overgrowth. What does it mean? That firstly, the trunk formed, then its growth was stopped by the precipitation of solid inclusion on its surface, and then the emerald growth start again, but can start from only in the place here, in the area here where the emerald surface was unmasked by solid inclusion, and then if the emeralds was able to grow on the solid inclusion and even to overlap them and develop laterally. So this is the way has the cap can form on the trunk. I mentioned you before the analogy with quartz, but in the quartz, the situation in the known sample of shattered quartz, the situation is a little bit different from these emeralds, because generally in the cap we have low inclusion and the cap is formed under low driving force conditions. Instead, here we can see that the cap is a little bit darker, so it contains more chromium and vanadium than the trunk, and it also has higher amounts of inclusion, both solid and fluids. So that means that it grew under higher driving force conditions. But drive condition, and the difference between the condition of formation from the trunk and the cap are due to the fluid circulation and other pressure I told you before, due to the geological context of this sample. Another particular sample found here is called vaso-emeralds. Vaso means cup because they look like a cup but without a hand. So they are characterized by a big central cavity or several small cavities, neighbor cavities in the middle of the sample. In this case, we also use the X-ray tomography, which show in this sample, for shown here in scale of gray, that there is not one cavity, but several cavities, one together the other one. And this creates inside the sample a surface that is not smooth, but is steep, and you have a kind of step developing parallel to the z-axis due to the proximity of these several cavities. And what is very nice, here you have the optical image of the sample, and next to it, in the gray scale, the image obtained by X-ray tomography, and you can see that the cavities are pointed bottom, and this is important information for mineralogists, because it means that they are formed by etching along line defects that are called dislocation. So it means that this area was rich of neighboring dislocation, and then the dissolution acted preferentially along this kind of defects. You can also see that the cavities are not developed along the entire crystal, but they stop nearly at the middle of this crystal. And this is because the dislocation, the defects are not extended through the whole crystal, but just in the upper parts of it. And optically, you can also see that the cavities underlined by the oil that is typically used to improve the clarity of emeralds stops here, and you have a kind of a trapping front that indicated two different portions of the crystal, one rich of inclusion with a slightly darker color, and the other one, the lower part, without inclusion and slightly green, light green. This means that the conditions during the development of this crystal are changed, and above all, after its formation, we have etching processes that change the final shape, the final aspect of these crystals. Here you have another case that is called spongy because it looks like a sponge. And we can say that this is a special case of basal emeralds because you have cavities, and you can see here on prismatic phase that the striation is due on the prismatic phase is due to the etching along the cavities, and so the steps are due to neighboring cavities like in the vasohemeral, and but the difference is that the cavities in this case come from the top to the bottom of the sample, and the cavities can also be filled by minerals typically of this geological context, as I said you before, pyrite and carbonates, in particular calcite and dolomite. And you can see here in the upper image, you have the filling is can fill completely the cavity or partially, and in this case you have the mineral just at the bottom of the sample. Another unique kind of sample found in this place are emerald replaced gastropods. So here you have fossils that are made by emeralds. So it's the unique occurrence of these kinds of fossils. Nowhere else you can find these gastropods. And how they form? So practically at the beginning you have the replacement of aragonite shell of these gastropods by calcite, and then when the circulation of fluids with high salinity I described you before arrive, they dissolved the calcite, and a healthy space, the imprint of this fossil was left. Later, the circulation of fluids interacting with the Blake shale released chromium, vanadium, and beryllium, so the precipitation of emeralds was possible, and emeralds filled this empty space, giving rise to this special fossil. But we also have to say that the preservation of these fossils was possible because we have Blake shale, so the future of the rock itself allowed to the the occurrence, the finding of these gastropods. So now we can go on the other side. On the western belts, we have compressive geological structure. So the kind of sample we can find here, due to the difference in geological situation, are completely different. And in particular, here you can find trappish emeralds, who are found only in 3 mines, Muzo, Cosquet, and Peña Blanca. So you can find real trappish emeralds only in these mines. Nowhere in the world you can find other trappish emeralds. Maybe you can find trappish like something sample that looks like trappish emeralds, but not the real one. So this is why they are so famous in the world. And together with trappish emeralds, we can also find the calcite, trappish emeralds, and horseshoe emeralds. The horseshoe emerald is just an incomplete group of prismatic emeralds, and you can see here the completed group is marked by the absence of some prismatic phase. You can see here, and the inclusion, the presence of big inclusion like calcite and B-terminated quartz. You can have the same image here, so you can see the particular shape of these samples and the inclusion with different density in the middle of this sample. Similar sample were described by Graziani and co-author in 18, and they are found from example in Brazil. This author described this sample as the results of different flow of fluid circulation. When you have a higher flow of fluid, the growth of the emeralds was how do you say normal one. So all the phases are developed. On the other side, so where the growth is incomplete, you have a lower, a weaker flow of fluid circulation, and these make these hamper the formation of prismatic phase and result in this particular habit of the sample. But now let's talk of the trappish emeralds. So how I said, the trappish emeralds are only found in Colombia and only in 3 mines. We were lucky. We had the opportunity to analyze and even to cut few of trappish emeralds, which are very rare and difficult to find above all for analytical study. So here you can see all the sample I could analyze in this work. But what it is the trappish texture? The trappish texture was, of course, described not with this name, but like a particular texture in the 19th century by a French mineralogist called Émile Bertrand, who who analyzed Colombian emeralds and was surprised to find these very strange emerald sample, but he could not really explain why they are formed in this way. The term trappish was introduced later, a long time later, by McGowan, who used the same word used by the Colombian former. So it's a Spanish word referring to a can crashing gears that you can see here, which looks like the texture shown by this sample. In fact, most of the sample are characterized by an hexagonal core surrounded by what are called dendrites, but you can see there are not dendrites in the sensu stricto mineralogical one. And these dendrites separated growth sector. So the result looks like a gear. We can cut few of sample and we realize that in some case you really have a core. In other case you don't have a core and dendrites cross in one point in the center of the crystal. And you can see here, you can see of course this intersection of the sample cut perpendicular to the z-axis. If you are lucky and your sample is big enough, you can also cut a section parallel to the z-axis, and you can see here the core form like a double pyramid. And this lets us think to this model to reconstruct the habit, the morphology of the crystal. So you have prismatic growth sector around a pinacoidal growth sector, which gives the double pyramids forming the core. And the presence or the absence of a core on a section perpendicular to the z-axis will depend on the section is cut. So if the section is cut exactly between the two pyramids, you will have no core. And depending on where you cut the section, the core can be more or less developed. So it's just a cut effect and not a problem of growth, the presence or absence of the core. To confirm our theory, we use the X-ray tomography, which, as you can see before, is able to give us a 3D vision of the whole sample, including what is inside. And here you can see the video. Yes. So this is starting from the top of the sample, going through the bottom. And you can see here that the model was correct. So you have a bigger curve at the top, and when you go inside through the middle of the two pyramids, the curve almost disappears. Sorry. This was what we are looking for, a scientific proof to demonstrate that our model was correct, and that is the case. We also see that what they are called dendrites are not dendrites like you can see in oxide for minerals, but it's just a name given the literature to for the similarities between the aspects, but there are nothing to do with the genetic formation, the genetic origin of dendrites and what we observe in the trappish sample. But in the literature, these terms is still present, so is still used in the description of trappish samples. Practically, what they are called dendrites are just accumulation of several inclusions, as you can see here around the core, then develop between the two growth sections and develop like a van at the hand in the outer parts of the sample. And this dendrite contains several kinds of inclusion, calcites, albites, pyrites. They can also have beryl and even a small piece of ostrox, so a piece of black shale that is often albitized, like I said you before. And the X-ray data also show that dendrites here you can see in a section perpendicular to the z-axis, but here you have a section parallel. The z-axis was along this direction, and you can see that dendrites develop laterally and protrude under the growth section. So they are not limited on the surface, but really they develop inside the sample. We also observe that in some sample there is another group entering the whole trappish, and the overgrowth is usually of a different color, and you can see here usually is darker, containing more vanadium or chromium. What does it mean? This confirms that during the formation of the trappish, we have a lot of change of chemical and physical parameters in the grow medium, and this explains this complex texture. We also did a technique that is not really used now. It's a kind of old, unusual technique for mineralogists, but sometimes it can be useful, and it's called X-ray topography. This technique just allows us to do a kind of radiography of the sample, showing the defects above all in the analyzed sample. And we did use this technique not really to see the defects, but above all to understand if we have one sample or several samples kept together. This technique proved us that we have a unique sample, and each trappish emerald is a unique crystal. So we can eliminate the hypothesis made in literature long time ago describing the trappish emeralds like composite crystals or twins. We can confirm that is only one crystal, but it is the result of a complex history strongly related by the geological context, spatial context of the Colombian deposits. And this texture is not only shown by emeralds, but it can be found in other minerals like castellite, as you can see here, ruby, garnet, tourmaline, and is what is called from the mineralogical point of view a combination of the textural sector zoning and chemical sector zoning. What this means? This means that you have particular growth conditions that change fast, so fast that the crystal, when develop its growth sector, that will result in the well-developed phase in the final habits, they will have some trouble in the growth, and then between the growth sector you will accumulate a lot of inclusion of whatever else is in the grow medium. So this is why you have other minerals and even piece of the host rock. And this will result in a textural sector zoning because the inclusion will mark each sector to the neighbor one. And then generally the the physical and chemical change in the grow medium results in a different absorption of chromophore cation in the beryl, and this will mark the different growth sectors, so the sectors that are not equivalent by symmetry, by a different chemical composition, so a different color at the end. And this is a kind of simple way to describe, to resume the complex history of the of the trappish. But if I go deeply in the detail, it will be even more and more complex and need more time to explain exactly how they form. But I just want to give you an idea of the complexity of the formation. And this also explains why they can be found only in this place. So to conclude, I can say that the formation of trappish emeralds and other oddities in these famous Colombian deposits are strongly related to the complex history, geological history, and above all to the fluid circulation that we have in this basin. So the fluid circulation change the pressure and the composition of the fluids will affect the growth on of these minerals, and these we can have the equilibrium between emeralds and fluids that change over time following the change in the fluids themselves. And this is why we can have growth perturbation and etching process, and even the combination of two that will give rise to this particular sample that cannot be found or rarely are found in other places in the world. If you want to learn more about that, I can suggest you a publication on on Journal of Gemology, and we did a short review of these oddities, but you can really read more about them in these special books concerning emeralds. So thank you so much for your attention and for your patience, and above all, I'm sorry for my English that is getting worse since I left USA. Thank you so much.
Thank you so much, Isabella. That was extremely interesting. I hadn't even heard of a lot of those different emerald oddities from Colombia. That was really cool. All right, we're gonna open up the floor for questions now. Does anybody have any questions for Isabella? Yeah, Bruce. I'll repeat it. We just got a question asking what the general scale is
The
for
size
these.
of sample?
Yeah, for the different samples and the different textures.
Yeah, they are very small, maximum 2 centimeters. Yeah.
Yeah, some like you can get they're really hard to come by and very expensive, but you can get really nice like Trapechi emerald cabochons, and you can get specimens of them. You just don't see them too often. Yeah.
Yeah, but they are very expensive.
Yeah. Otherwise, I would have some. Yeah. Any other questions? Yeah, we've got a question here. I'll hand the mic over.
Yeah, I'll come over here so you can see me. So I'm just still trying to wrap my mind around all the, the formation of the Trapechi texture is very interesting, but it sounds very complicated. But I guess it sounds like a key part of this is you're in a compressional setting. And so are those compressional stresses are modulating the crystal growth in some way, and that's what's in part.
Yeah, but also you have the pressure of fluids that change over time, but also is what you see, the rate of this change, because sometimes you have change that are so fast, and then you can have that what is called the Berge effect. So you have a faster growth on the corner of the hexagonal core, and this is why you can incorporate it more solid inclusion. So in this way, in this direction, the growth is faster. And then just so suddenly you can have the normal growth of sector that are green emerald in between these portion called dendrites. So it's very complicated, and it's very, obviously, fast and rapid change around the emerald.
Yeah, and so
fluid pressure. Yeah,
fluid pressure is an important part of that.
To synthesize them due to this fast change in the grow medium. Yeah.
Yeah. Okay. Gotcha. That's interesting. Cool. Should we? Oh, Anne has a question. Yeah.
Any other questions from the audience before I go for it? All right. So I know you touched on it, but there's a lot to take in there. If you could, did you say there was you had discovered why you have that inverse pyramid effect throughout the beryl crystals, or is that related to the, yeah, I guess just why do you get that inverse pyramid texture?
You have, because you have two pinacoidal phase. So you have that in a whole beryl, so but you cannot see because you don't have inclusion that mark the limit of this sector. But you have in all prismatic beryl is just the area corresponding to the pinacoidal phase. And as you have two opposite one, you will have two area that form like a kind of pyramid, opposite pyramid.
Okay, gotcha. That's fascinating. Yeah, all the inclusions just highlight that so well. Very cool. All right. Well,
I'm just kind of spitballing here a little bit, which means I'm just kind of throwing ideas out there. But we had a talk by Caleb yesterday about fadens and the role of, tectonic of varying tectonic pressures in forming photons. I'm kind of wondering if there's something similar going on here, the importance of tectonic pressure influencing fluid pressure, giving rise to these weird textures that we're seeing.
Exactly.
Yeah, it's
Yeah, exactly. And this is why even in Colombia, you cannot have trapeze in the other mine. You only have in 3 mines of the Western Belt because you have a global tectonic, but also local tectonic that is very specific. So you cannot repeat the formation of this mineral in other places.
Yeah, that's super cool. Super interesting. I'm going to hand it back to Anne. Any other questions?
All right. Looks like everybody is just dumbfounded by all the crazy emerald textures. Thank you so much, Isabella, for joining us all the way from France. That was wonderful. And yeah, we'll send you a copy of the program soon and links to all the other talks so you can.
Thank you so much for the invitation. It's a pleasure for me.
Yeah, thank you. Give Isabella
Bye-bye.
another round of applause. All right. Thank you so much.
Yeah, you want to stop the recording really quick? And